So this process is called modal analysis, okay, or theoretical modal analysis. And we'll start just by taking the standard equation of motion for an undamped vibration system. Okay, so there's no damping term in here. We've got mx double dot plus kx equals 0. There's no force here. But that's, we all know that equation. This is in matrix form, which suggests that we're dealing with more than one degree of freedom. Okay, got a mass matrix and a stiffness matrix, and those x and x dot are vectors representing displacement and acceleration. And we can make the substitution. Okay, we know it's going to oscillate, so it's going to be a sinusoid, okay, of a certain frequency omega. And you substitute that in, and we get what's known as the eigenvalue problem. Okay, and we covered this last week, as expected. And the thing is, we want to work out what this is, okay, which is our mode shapes, and we want to work out what this is, which is our natural frequencies. If we've got a force system, obviously that 0 at the end there, okay, is turned into a forcing vector. And the problem with this system, okay, is that these equations are coupled together. K, in particular, will not be a diagonal matrix. What do I mean by a diagonal matrix? Well, basically, a diagonal matrix has values down the diagonal, and all the other terms are 0. Okay, and with K, you've rarely got a diagonal matrix. It's always going to have values off the diagonal. Okay, so basically, your equations say you've got 2 degrees of freedom. The motion of x1 will depend upon the motion of x2, and vice versa. Okay, if K was diagonal, then the equation for x1 would just have x1 terms in, and the equation for x2 would just have x2 terms in. Those equations would be uncoupled. But the thing is that with multiple degrees of freedom, they are often coupled together. Okay, you can't separate them. And like I said, with 2 degrees, that's okay. With 3 degrees, it's not too bad. But you go beyond 4 degrees of freedom, and the thing becomes virtually impossible to solve by hand. Okay, and it becomes very complex and difficult. You've got to solve these equations simultaneously. So there's a process that we're going to deal with. And that process involves uncoupling these equations, okay, of motion to give a set of individual second-order differential equations that you can solve individually. So they don't have to be solved simultaneously. Okay, so you go through and solve them, and then you come out and you convert them back to displacements. Okay, you combine those individual solutions to give the actual response of the system. So here we've got an equation that's dealing with x, and what we do is we convert it to deal with a different term. We'll call it a modal variable, and we'll see that in a moment, okay, which will give us these equations. You can solve those equations, and then you convert it back to give us x, which is our displacement, which is what we're interested in finding out.